The question is, could you illustrate the use of calculus to find geometric properties via simple examples? So let's be clear about just exactly what is it that we are interested here. Limiting ourselves to two-dimensional sections, we are interested in centroid, second moment of inertia, and polar moment of inertia. If you recall from the theory videos, these are the equations for finding these quantities. My first example concerns a rectangular cross-section shown. The first question is to determine the location of the centroid with respect to the xy coordinate system shown. I'm going to show you how to do this by calculus in a second, but first let's remind ourselves that there is another way to find this also. Recall that in the theory videos we also proved that the centroid must lie on lines of symmetry if ones exist. For this simple shape, it's clear that this line is a line of symmetry and this line is a line of symmetry, and therefore C here, which is the intersection of these two lines, must be the centroid of this section. And therefore the coordinates of the centroid with respect to this xy coordinate system are these. X bar is b over 2 and y bar is d over 2. Now let's do this by calculus. The key in using calculus to solve problems like this is to define this differential element in the most efficient way. In this particular case, it's fairly straightforward. We go to a point which has the coordinates x and y and define the differential element such that its sides are parallel to the x and y axis. So this will be my differential element whose area is dA. And dA here is simply dx multiplied by dy. And if you recall, this is the formula for finding x bar, right? So let's go ahead and expand this and see how it pans out. Here are the steps. dA here is dx times dy, right? And therefore it becomes a double integral because there is both x and y in this integration. So since the variables are uncoupled, we can separate the integration into something like this. Integration involving x and integration involving y as two separate terms. And similarly in the denominator, dA is simply dx times dy, which also can be separated like this. Each of these integrations can be performed independently, and that's what I have done over here. X times dx integrated becomes x squared over 2, right? 0 to b for x and 0 to d for y, right? So you perform all of these integrations and apply the limits, and we end up having b over 2 for x bar, the way it's supposed to be. That's what we found out over here using the theory based on the lines of symmetry, right? Here is the step for y bar. We get y bar equal d over 2, like it's supposed to be, right? Our question number 2 for this section is to determine the second moment of inertia about the centroidal axis x. In other words, this time I'm placing my x-axis right through the centroid C. I'm going to show you how to do this in two different ways. In the first method, we follow the same approach that we followed in finding the centroid. I'm taking my differential element at a point that has coordinates xy, just like this. So my dA would be simply dx times dy. And if you recall, this is the formula for finding Ix. Remember, we had to put y here when we find Ix. In other words, when you find the second moment of inertia about this axis, we had to use the coordinate that is perpendicular to the axis, which is y, right? Here are the steps which leads to the expression of 1/12 BD cubed for Ix. The steps are very similar to what we did in the earlier slide. I'll let you follow. Just note the limits here. Limits for y is minus d over 2 to plus d over 2. And limits for x is minus b over 2 to plus b over 2. Also note that integration of y squared is y cubed over 3. In the second method, instead of taking a little rectangular differential area like we did in method 1, I'm taking a strip that is parallel to the x-axis. The width of the strip is dy, and therefore dA would be simply b multiplied by dy. Now using that expression for dA in this equation for Ix, we find that the integration is now a single integration and not a double integration like we had in method 1. In other words, we simply have dy in this integration, not dx times dy. As expected, carrying this integration through and applying the limits, we end up with the same expression for Ix, which is 1/12 bd cubed. And if you try to find Iy, you will find that these two variables will be flipped. We will have 1/12 d times b cubed. So what's the easiest way to remember this? Well, b here is the dimension parallel to the axis about which we are seeking the second moment of inertia. And d, the dimension that is being cubed, is the dimension perpendicular to that axis. In our example number 2, we have an area whose boundaries consist of two straight lines and a curve. And this curve is given by this mathematical function, y equals c times x to the power of 4, where c is a constant. The x and y coordinates of this endpoint are little a and little b respectively. We'll try to do this in two different ways. In the first method, I'm going to take my little differential strip to be vertical like shown here. Even though y coordinates of this point is different from that point, since this is a differential area, dx is supposed to be extremely small, right? So in that case, dA can be simply taken as y, which is the y coordinate of this point multiplied by dx. Substituting this for dA in our formula for x bar, we have this. These are single integrations. We only have dx in these integrations, not dx times dy, right? Therefore, we need to express y as a function of x in order to perform these integrations. Now remember, y is the coordinate of a point that lies on this curve, right? Y is the coordinate of this point, right? And for any point on that curve, this expression is valid. Y equals c times x to the power of 4. Alright, substituting this for y, performing the integrations and applying the limits, we end up having this expression for x bar. X bar is 5/6 a. In the second method, I'm taking my differential strip to be horizontal like shown here. One thing you want to be careful about this formula for x bar is that x in this formula, x in this expression, is the distance to the centroid of the differential area. Now here, this is the differential area, right? The centroid will be in the middle of that, right? And therefore, x to be used in the integration that we have in the numerator is this distance, which is the average between x and a, which is x plus a over 2. Now here are the remaining steps. Took a while to get to the final answer, but we do get the same result. X bar is 5/6 a. Steps are fairly easy to follow, so I'll let you do that. One thing I want to point out is that when I went from this step to this step, I expressed b as a function of a. Now remember, for every point on this curve, the x and y are related by this function, right? So that should be true even for this final point, where x is a, y is b, right? So if I substitute those values in this expression, we get this relationship between a and b. Right? So in this step, that's what I used. I used b equals c to the power of c times a to the power of 4 for b. So that allowed me to keep everything in terms of a, and finally we get a simple expression for x bar like it's supposed to be. So you can see in this particular case, between the two methods, method 1 is a lot simpler than method 2. Our third example is to determine the polar moment of inertia of a circle like this one right here. Recall the formula for the polar moment of inertia about the z-axis, which is this, right? And here rho is the radius of the differential element, dA is the area of the differential element. The integration is to be carried out throughout the cross-section. The easiest way to perform this integration is to consider a circular differential strip like shown here. This strip is taken at a radius rho, and the thickness of the strip is d rho. The area of this strip can be approximated by this equation where 2 pi rho is the circumferential length, right? And you multiply that by d rho, which is the thickness of the strip. Here are the steps. We use this for dA in this expression, and the limits for the integration is 0 to r, which will cover the entire circle. The integration itself is very easy to perform, and I'll let you follow. And what we get is jc equals 1/2 pi r to the power of 4.